Hello. Our bell ringer question today is, predict the ions formed from the following elements and the formula of the ionic compounds that they form. Hopefully by looking at the periodic table and the valence electron compositions of strontium and oxygen, you are able to determine that we should end up with strontium 2 plus, oxygen 2 minus, to form the ionic compound strontium oxide. Today we're going to be talking about covalent bonding in greater depth, and our learning objectives are: I can describe the covalent bonding model, I can compare the bond orders, lengths, and energies of covalent bonds, and I can describe bond polarity using electronegativity, polar arrows, and partial charges. We've already talked briefly about the basics of the covalent bonding method. Basically, the covalent bond is a sharing of electrons, with the sharing of those electrons being localized between the two atoms. So if we look at this relief diagram over here, we can see that around the nuclei, that is the area where we see the greatest electron density. However, when we have a covalent bond, we also see an increase in electron density between the two nuclei. And why does covalent bonding occur? Well, it helps atoms satisfy the octet rule, which I believe I've mentioned briefly, but we'll dive into a little bit more deeply here. The octet rule is the idea that many atoms want, obviously, we can have a whole nother discussion about atoms having free will, but the idea that atoms want to have 8 valence electrons in their valence energy level. And this, if you think about the S and P energy or subshells, this makes a lot of sense. We can have up to 2 electrons in our S subshells, and we can have up to 6 electrons in our P subshells. So that means they're looking to get 8 total. And when we have a covalent bond, each atom counts a shared electron towards their octet. So if you look at this diagram right here, where we've got our hydrogen bonding with our chlorine, hydrogen has 1 electron, and it is sharing that 1 electron with chlorine. So chlorine now feels like it has 8 total electrons. Obviously, hydrogen and many other elements in the S block have a valence subshell that is an S subshell, so they can only have up to 2 electrons there, which is why those elements tend to form anions. They tend to, cations. They tend to lose those electrons. When we are discussing a covalent bond, we talk about the shared pair or the bonding pair and the lone pairs. So again, if we go back to this example, this circled pair of electrons is the bonding pair or the shared pair. And hydrogen doesn't have any lone pairs, but if we look at chlorine, there are 3 lone pairs of electrons. And when we're writing and drawing Lewis symbols or Lewis electron dot diagrams, we always make sure that our electrons are paired when possible, because that is how they tend to exist. And we know this from when we were filling our electron orbital diagrams. Electrons like to exist in pairs when they can. We can have several different bond orders and types of covalent bonds. Bond order is the number of electron pairs being shared. So that is, again, that shared pair, that bonding pair of electrons. We can have single, double, and triple bonds. A single bond has a bond order of 1 because it has 1 pair of electrons that's being shared. A double bond has a bond order of 2 because there are 2 pairs of electrons that are being shared. A triple bond has a bond order of 3 because 3 pairs of electrons are being shared. It's very important to remember that the bond order is dictated by the number of pairs of electrons that are being shared, not the number of electrons being shared. Pairs of electrons being shared. Here we can see 2 different examples of how to represent different bonds, different single, double, and triple bonds. If we look at our hydrogen and chlorine, we can draw a Lewis electron dot diagram, and I've drawn a red circle around the hydrogen and a black circle around the chlorine to indicate which electrons are being felt as belonging to each atom in that covalently bonded pair. We can also depict that same bond, that same single bond between the hydrogen and chlorine with a single line. However, if we are drawing a Lewis symbol, it is correct to include all of the lone pairs, which is why hydrogen is all by itself with the line, the bond connecting it to chlorine, and 1, 2, 3, 4, 5, 6, 3 lone pairs of electrons around chlorine. Here we've got C2H4, and C2H4 has a double bond, which is a bond order of 2 between the 2 carbons, and then 1, 2, 3, 4 single bonds with hydrogens. So its Lewis symbol will look like this, with carbon 2 bonds, double bonded, and then 1, 2, 3, 4 single bonds with the surrounding hydrogens. And again, it has a bond order of 2 as compared to the bond order of 1 in our hydrogen and chlorine single bond. Finally, we've got N2, our 2 nitrogens that are sharing 3 electron pairs. They're sharing 6 electrons between them for a triple bond. So each electron will have a lone pair or 2 extra electrons outside of the triple bond in the middle. And if we think about each of these examples, all 3 of them help satisfy the octet rule for all of their elements. We look at chlorine. Each bond counts as 2 electrons towards each element to which it's bonded. So chlorine has 2, 4, 6, 8. Octet rule fulfilled. For each carbon, 2, 4, 6, 8. Octet rule fulfilled. And since this atom is a mirror image, we know that all of them will have the same octet rule fulfillment. And again, for the final nitrogens, 2, 4, 6, and 8. With ionic compounds, we talked about the incredibly strong attractive forces between oppositely charged ions and how that generates creates a very strong exothermic reaction when an ionic solid condenses from its gaseous components. With covalent bonds, we're going to talk about the bond energy, which is the enthalpy change accompanying the breakage of a given bond in a mole of gaseous molecules. So just like lattice energy is formally the breaking up of a solid into its gaseous molecules, bond energy is the breaking of a covalent bond. When it comes to covalent bonding, we aren't overcoming any incredibly strong ionic forces, but we do have to consider the fact that the nuclei of the atoms that are bonding are going to repel one another. The electrons in those atoms are also going to repel one another, but the atoms are able to strike a balance between those repulsive forces and find that kind of sweet spot where you get the attraction between the gained electron to each nucleus. And that is why we have bond energy. So bond energy is always going to be a negative value when a bond is created, when bonding happens, and it's always going to be a positive value, just how bond energy is depicted here. Bond energy of a bond breaking is always going to be a positive value. Again, similarly to ionic compounds, we can talk about the distance between 2 nuclei. In this case, when we're talking about a covalent bond, we're discussing the bond length, which is the distance between the 2 nuclei of bonded atoms. And of course, bond length is definitely going to depend on the size of the nuclei that are involved in the bonding, as well as some of the repulsive forces of those nuclei and the repulsive forces of those electron interactions. When it comes to covalent bonds, we can see some pretty interesting relationships between bond order, bond length, and bond energy. This table is pulled from right from your textbook on page 353, so feel free to take a look at that at some point. But if you look generally across the board, some general patterns that we will see is that higher bond order, so triple bonds, double bonds, triple bonds, will generally have shorter bond lengths and higher bond energies. So that would mean that it would those atoms are being held together much more closely and much more tightly, which, again, if you think about it, makes sense. We've got those nuclei that are pulling very strongly on those valence electrons in double and triple bonds. Generally speaking, when it comes to single bonds, the longer the bond length, the lower the bond energy. If electrons are being held much further away from the nuclei of the atoms to which they're bonded, those bonds are going to be easier to break, generally speaking. A lot of these trends, if you look at a periodic table, follow a lot of other periodic trends with things like atomic size and electronegativity, which we'll talk about next. So if you look at a periodic table, you can see a lot of the reasoning for the different trends that we're able to see in this table. As I just mentioned, we're going to talk about electronegativity as well. So electronegativity is the ability, as I just mentioned, we're going to discuss electronegativity. Electronegativity is the relative ability of a bonded atom to attract the shared electrons. So this should not be confused with electron affinity, which, as you remember, is the essentially the ability of an atom to become an anion, to be negatively ionized, so to take on an additional electron, which is not the same thing as sharing an electron. So electronegativity is only a trait that we see in bonded atoms. Because some atoms have a higher electronegativity than others, we see uneven sharing of electrons. So we see what's called polar bonding, where those electrons are not perfectly in between the two nuclei, but rather they are a little bit closer to one and further away from the other nucleus. Electronegativity is not something that is formally measured, but something that has a relative scale. The highest or the most electronegative element on the periodic table is fluorine. And so fluorine has an electronegativity of 4, and the scale is then from 0.0 to 4.0. And as I just mentioned, electronegativity leads to bond polarity. So there are two different types of covalent bonding that we can see. We can see nonpolar covalent bonds in which the bonding pair is shared equally between the two nuclei. And this happens when the two nuclei are of identical atoms, the same element. So any sort of diatom, Cl2, O2, C2, N2, any of those will have a nonpolar covalent bond. However, we also see polar covalent bonds, which is the unequal distribution of electron density, because one of the elements in that bond is more electronegative than the other. It gives the bond partial positive and partial negative poles. So in this picture right here, we can see a nonpolar covalent bond in which the electrons are shared equally. This is the electron cloud depiction. And here in a polar covalent bond, we can see the partial positive and the partial negative unequal sharing of electrons. So between the two nuclei, this atom will feel a partial negative charge, and this atom will feel a partial positive charge. It should be very clearly delineated. This does not mean that this acts as an ion. It does influence how those molecules will interact with other molecules. If you've ever thought about like surface tension in water, this is a great depiction of why that occurs, because we do see a slightly negative charge and a slightly positive charge within the same molecule. So they're going to interact with other molecules based on those partial charges. When we are drawing a Lewis symbol, we usually depict partial polarity with a polar arrow. We can also, instead of a polar arrow, we can also use the partial positive, partial negative symbols. And this is just a lowercase delta with a plus and a lowercase delta with a minus. let's talk about some of the unique properties of covalently bonded molecules. One thing that I really want to mention right up top, because it has a lot to do with all of the other, with a lot of the properties that we see in covalent molecules or covalently bonded molecules, is I want to differentiate between the strong bonding forces and then the weaker intermolecular forces. So again, when we were just talking about polarity, we understand that different molecules will interact with one another because they have those partial charges. However, it takes a lot of energy for the individual atoms in a molecule to actually break away from that molecule. So that helps to explain why we see things like a lot of covalently bonded substances that are gases, liquids, or low melting solids, because all of those individual molecules are able to break out of a very regular structure and become liquids or gases, or to melt at a very low temperature, but still maintain their molecular integrity. When we add a lot of energy, then we can finally get them to boil and disassociate those individual atoms from the structural molecules. Many covalently bonded molecules are also very bad at conducting electricity. We do see a very unique subset of covalent molecules called network covalent solids, and that's what the depiction is on the screen. That is diamond. So it is carbon that is in a very regular crystalline structure. And network covalent solids tend to be very, very hard and have very, very high melting points. Perhaps you know that diamond is the hardest naturally occurring substance in the world. And I've never heard of anyone trying to boil a diamond. They have very high melting points and are very, very hard because of their regular structure.